Hello. In the prior two sections, we've been constructing confidence intervals for population means, average values. The first day we talked about how we use a z distribution or a z interval when we know the population standard deviation, we have large sample. Or the second day we realized, hey, if you don't have a large sample or you don't know the population standard deviation, you need to be a little bit more liberal. You need to be a little bit wider when making your intervals. So we use what's called a t-distribution. So I would like to just try a warm-up question, make sure you understand the difference before we move on to the last type of intervals that we'll be constructing for not population averages, but population proportions, percentages. So try the following scenario. A vet is testing the body temperatures of dogs and finds the average temperature to be 101.5 degrees for the sample of 40 dogs. Sample standard deviation is 2 degrees Fahrenheit. Find the 95% confidence interval for the average body temperature if you use a z interval or if you use a t interval. Both of them are valid in this case because we have a large enough sample. We do have the sample standard deviation, so technically the book would say you should be using a t interval. Both would be valid in this case because our sample is large enough. But really you should be using the t interval for this. But let's see if you did both, how do they compare? So find the 95% confidence interval for a z interval and a t interval. Also explain why one is wider than the other. So pause the video, try it, see if you're prepared for what we're about to talk about today. Here's what you should have found. You should have found that the z interval goes from 100.88 to 102.12, and the t interval goes from 100.86 to 102.14. You'll notice this one is 0.02 wider, not very much different. That's where I'm saying honestly either one would be valid in this case because the sample is large enough. The t interval is probably more appropriate if you're following the book suggestion, but the reason the t distribution is a little wider is because it has wider tails. That was the whole idea, was that it's better when we have smaller samples. So you have to go further out to capture 95% of the data because its tails are a little bit wider. Because of this, your t critical will be greater than your z critical, and your confidence interval will be a little bit wider as well. So that was the whole idea of a t distribution, is that it was developed to be more representative of the normal distribution, and the normal was assuming you knew things that you didn't. So now let's talk about what we're going to be doing today. So in the prior sections, we were concerned with finding a confidence interval to estimate a single number, an average value, but now we're going to be doing it to do a percent. So it may have been in the prior cases that we were doing average house price, time spent on a project, repair costs, average coffee temperature, whatever it may be, white blood cell count. However, what if we aren't concerned with an average number, but instead an average proportion, a percent of the values? For example, what percent of adults are going to vote for a specific candidate in the next election are very important. And that's the number one case where this type of analysis is conducted, is testing the validity and giving range of values and expectations from surveys. A lot of the time it could be market research for a product or political research. So the population proportion is the probability of success in a single trial of a binomial experiment. We're essentially talking about binomial experiments because people are going to be either saying yes or no to something, success or failure. The true population proportion is P. We don't know that value. I don't know the exact percent of people that are going to vote for a certain candidate or vote for a certain proposal. So what do we have to do? We have to use a point estimate. The point estimate for P is denoted by P, and we put a little I guess it's an arrow. It's really called p hat in mathematics. It's a p with an arrow over the top of it. That denotes that it's an estimate, just like when we did averages, it was x with a bar over the top. That means average for a point estimate. This is going to be the proportion estimate. Well, we use it from the sample. It's the number of successes in the sample divided by the total number of the sample. It's read as p hat. So the population parameter is p. We estimate it with our sample percentage. Denote failure is what it's always been. It's 1 minus the success rate, and we denote it as Q hat. It's our failure estimate rate based on our sample. To construct a confidence interval for the population proportion, well, we take our point estimate, this should be P hat, and we add or subtract it from, our error margin of error from that estimate. Our margin of error is found from the following calculation. We're going to take a z critical score and multiply it by the square root of p times q, which are our point estimates from our sample, divided by n. And recall, This is almost identical to what we did when we were doing a confidence interval in the prior section. We took our critical score and we multiplied by the population standard deviation divided by the square root of n. So we're going to get the same place here. We take the standard deviation if it's a binomial. So this right here occurs from our binomial situations, which we did a few chapters ago, square root of n times p times q. To get these to talk to one another, they both need to be under a square root. So n is really the square root of n squared. If they're both have square roots, I can write them underneath in single square root. Then I know n over n squared is just n down below. And that is where we get our population proportion standard deviation, which is what we use right here in our margin of error. So that's how we find our margin of error, just like we did before. The steps that we go through are the following. We first identify the sample size and the values that are given to us. Step 2 is find the point estimate, usually given to you, or you would need to find it by taking how many said yes divided by the total. And then we have to verify that we can use a normal distribution to estimate, because we're using a z-critical score. And this comes to us from prior chapters. If we have a binomial, in order to estimate a binomial with a normal, we needed n times p and n times q to both be bigger than 5. Well, here it's going to be n times our estimate of p needs to be bigger than 5, and n times our estimate of q needs to be bigger than 5. That's so that we can use a normal distribution since we're using z-scores. You can find the critical z-scores by using the table or inverse norm. We're going to be using the calculator. Then you would find your margin of error, and then you'd add and subtract that margin of error from our point estimate. So all of this can be done on the calculator. You can also do the steps above, but we're just going to be using the calculator. You go to stat tests like we've done before. You're going to select option A. It's a 1 proportion z interval, and then you enter the inputs. Be aware this is different than selecting option 5, which is 1 proportion test. Do not select that. We're constructing z intervals, so it's option A. You have to scroll down further. Example, let's say in a recent survey, 627 out of 1,100 U.S. citizens surveyed said they were planning on voting for candidate A in the next election. Verify you can, and then construct a 95% confidence interval for the population proportion, then interpret the results. In order to use a normal distribution, we need n times p and n times q to both be bigger than 5. Well, we don't know p, so we have to use the estimate from our sample. N, how many people were in the sample? Well, 1,100. 1,100, another 0. There we go. P is our success rate. Well, that was 627 out of 1,100. And you'll notice, hey, these are going to cancel out. This is going to be just 627, which is definitely bigger than 5. So this one's going to work. N times Q, again, 1,100. Times our failure rate. Well, failure would be the opposite of success. If 1,100 were sampled and 627 said yes, if I subtract 627 from 1,100, that means 473 said no. Where did I get that? That was 1,100 minus 627, 473. That's how many people said nay to candidate A. Hey, the 1100s cancel out, it's 473, so n times p and n times q are just the number of successes and the number of failures. This is 473, much bigger than 5, so we are valid using a normal distribution. You would say since np and nq are greater than, does it say or equal to? I think it does say or equal to. It's much bigger, but we should probably write the definition, than 5. We can use a normal approximation. Step 2, you would use the calculator. Just to show you, we're going to do it by hand once so you understand the process and you'll appreciate what the calculator is doing. So here we go. Let's find our margin of error. Well, actually, let's do the point estimate first. Our point estimate is the percent that are going to vote for candidate A. That was 627 out of 1,100. Well, 627 divided by 1,100 is 57%. That's going to be the center of our confidence interval. Now we need to know how wide our confidence interval is. We call that the margin of error. We are constructing a, what did it say, 95% confidence interval. That's a z-score of 1.96. Now we need to multiply by the square root of p times q times n. P is our estimated success rate, 57%. Q is our estimated failure rate, which would be 43%, divided by our sample size. Sample size, 1100. Now you would just need to grab a calculator. So square root 0.57 times 0.43, all divided by 1100. I'm getting 1.96 times 0.1493. And then I take that, multiply by 1.96, and I get my margin of error 0.03. 3% it looks like. So that means if I'm making a 95% confidence interval, add 3%, I'm going to be at 60%, subtract, I'm going to be at 54%. So I would expect that the true percent of people that are in favor of candidate A is somewhere between 54% and 60%. And that's good news for candidate A, because you need more than 50% to win an election, and a 95% confidence interval has got them between 54 to 60. So if you're on that campaign, thumbs up. If you want to do this in the calculator, you would go to 1 proportion z interval. You would enter x. What is x? X is the number of successes, which was 627. N is our sample size, 1100. And the confidence level is 0.95. Let's actually do it. Let's show it. So where did we go? Stat. Did I say over to test? I think that's right. Then we're running, don't choose option 5. That's a proportion z test. We're doing intervals right now. We'll get to tests later. Instead of option A. A is the first one past the numbers, past 0. Hey, there it is, 1 proportion z interval. Our x was 627. Hopefully I'm typing, yep, then 1100 was in our sample, and is the sample size. Our confidence level, 95%. Calculate that guy. Hey, look at this, 54 to 60%, just like we had before. Or interpret our results. We would say with 95% confidence, you can say that the population proportion, which we didn't know, we had to estimate it. Maybe should have pointed that out when we were doing this. We don't know P, right, when we're doing this. That's the whole idea. I don't know P, so we had to use our samples percent to estimate what actually P is. We can say that the true population proportion of U.S. citizens who plan on voting is between 54% and 60%. You can either write these as percentages or decimals, that's fine. So there you go. That is how you construct a confidence interval for a population proportion. I'll have you try. In a survey of 1,000 community members, so instead of voting for a candidate, let's say that they're going to vote for a proposal, like a school levy, to build a new school, like recently occurred in East Helena. First, verify you can, then construct a 95% confidence interval for the population proportion of community members who support the school levy. Give it a try and come back and see how you did. Okay, this is what you should have found. You should have found n times p, well, 662, and 338 is n times q, so much bigger than 5. You run the confidence interval, and you'll get the confidence interval is between 63% and 69%, so looks pretty good to pass if you were on that committee. If you were on that committee and you got something like 43 to 49%, you might want to start knocking doors and talking, because that's below 50%. So this gives people an idea of where they're at before the actual election. So the interval, or the interpretation, you would say, is with 95% confidence, you can say that the population proportion of community members who support the school levy is between 63.3% and 69.1%. I didn't do it in the last example, but it probably always is wise to go out to 0.1%. Just like we did before when we were talking about constructing confidence intervals for a point estimate, you also want to know how many people you need in your sample if you're going to be constructing a interval for a proportion. Same process as before. We did this recently. I take my margin of error equation and I'm going to solve for n to find what my sample size would need to be in order to obtain a certain margin of error. In order to do this, similarly, I'm going to first divide both sides by z critical. So I would end up, I'm trying to solve for n, I get E divided by z critical is equal to what? Square root of PQ. I'm going to split them up, divided by the square root of n. Back in algebra, hopefully you learned that the square root of a over b is equal to the square root of a divided by the square root of b. If you don't believe me, try it with 16 over 4. And once I have this proportion, I'm trying to solve for n. Maybe I can use the cross product property. Multiply z critical up, multiply square root of n up as well. I'm undoing division on each side. Similar process we did when we were solving prior. Last step before I have square root of n by itself, and then I just need to square is divide both sides by e. I then get the square root of n is equal to z critical times the square root of pq, all divided by e. Now I just need to square both sides. Square this side and square this side. And you'll see the formula, if you look it up, is this. The sample size is equal to z critical squared over e squared. And then the last thing is this squaring will cancel that square root. So we just get pq. These are PQ hat. I kind of dropped those as we were going through it though, but that should have been implied. And there you go. That's the formula that we use. So here's an example. Let's say you're running a political campaign, because these are #1 place these things get used, and you want to estimate with 95% confidence the proportion of registered voters who are going to vote for your candidate. Your estimate, you want to be accurate within 3% of the true population. You want your interval to be 3% wide on each side, so I guess 6% total. Find the minimum sample size you would need if there's no preliminary estimate available. So you have no idea if your candidate is favored by 40% of the population or 65%. Well, if you don't have an idea, then the best thing that you can do is estimate that the percent of success rate is 50%. That's what we do. So the sample size formula I'm going to run, what we derived a second ago, is given right there. And I just enter everything as I know. I know for 95% confidence interval, z critical is going to be 1.96. I want margin of error to be 3%. So my sample size, my point estimate for my population success rate is 0.5. Well then, if 50% failure, or success, 50% failure, 1.96 over 0.03. That's important. I should note your margin of error is always entered as a decimal, and then you square that. And when we do it, just save a little bit of time, you end up getting the sample size needs to be 1067.1. You should not round that down because I need at least that. So it's going to be 1068 people who need to be involved in the survey in order to get a 95% confidence interval with a margin of error of 3%. I'll have you try. Rerun the following calculation to determine the minimum number required for a survey if we estimate our candidate is favored by 69% of the data. So that means now that P is no longer 50%, we have an estimate. It is 0.69. Explain why the sample size number that you get is either lower or higher than our previous one when no preliminary estimate was available. That's why we had to use p hat before is 50%, 0.5. So rerun the calculation we just did, tell me what you get, and explain why. So here we go. You'll find you need at least 914 voters. This is less than the prior because we have extra information. We have an estimate for P now, and because we have an estimate, we don't need to have as large of a sample. So there you go. That is it for today. Thank you very much.